About a decade ago, the U.S. government decided to extend the lifespan of the Ohio-class ballistic missile submarine. And as part of that life extension, they wanted to redesign the guidance package, the electronics guidance package for the sea-launched ballistic missile, the Trident II. So the concept was to apply our academic research to the real-world problem that the Navy had of designing a robust guidance electronics package. And to do that, we needed engineers. And so the concept of ISDE was born, of creating a conduit for basic and fundamental research to be applied to real-world problems through engineering applications.
ISDE is an organization that analyzes and designs electronics that are going to be used in high reliability applications, especially those where they might be exposed to radiation. The main example of that is electronics that would be used in spacecraft, because once they get outside the Earth's atmosphere, they're no longer protected from all of the high energy particles that are flying around out there. So we design and simulate electronics to understand what the effect of those particles is going to be on the operation of the electronics.
We operate much like a small business. We have a fairly unique arrangement that involves academic research, industrial partnership, and entrepreneurship.
We have the largest group anywhere that works in this particular area of application, radiation effects on electronics. So we've got people that span the range of activities from atomic scale physics up through system design.
One of the programs I've been working on is Rad Hard by Design, where we use design techniques to harden circuits for radiation environments. We want to provide designers with tools that allow them to easily prove their devices and designs before going to fabrication, which results in a cost savings to the programs and more confidence in the design before it gets fabricated. We've seen a lot of success out of this program. We've developed some models that have allowed designers to really understand what their designs will look like ahead of time, and we've seen a lot of first-pass success in circuits that have gone on to prove themselves to be radiation hardened.
So the goal of the CubeSat program is to verify predictions that are being made here on the ground. So we use accelerator facilities to characterize parts and predict on-orbit response. And the CubeSat platform allows us to put those parts into space and actually test those predictions. We have two successful programs right now, one with St. Louis University and one with AMSAT in placing experiments on those satellites.
Through our partners, we have access to the most advanced technologies, and we can analyze and test them and build models for those technologies that then allow us to be proactive and allow our sponsors to be proactive when they're building electronics using those technologies.
We do a lot of testing, both of things that we design and things that are provided to us by some of our collaborators. And a lot of the testing is done here on campus. It's a very fast and efficient way for us to characterize new technologies. One of the most interesting things that we're doing is to understand the response of emerging technologies, and that ranges from two-dimensional materials to new memory technologies. I think the key advantage that we have is that we have such a broad range of expertise that we can bring to bear on these problems.
It's very important for research to be applied because that's where the rubber hits the road. That's where the research actually impacts systems and our sponsors and their needs.